In this video, we'll see some of the applications of analog multipliers. In the last video, we saw how analog multipliers are built. These circuits are very important because in many real-world applications we need the product of two signals and they make it possible. The first application we'll see is a squarer circuit. As the name suggests, we want to generate the square of a given signal. As squaring is the same as multiplying a quantity with itself, if we feed the same signal Vx to both the inputs of a multiplier, then the output will be proportional to the square of the signal. If the scaling factor is k, the output will be Vx squared by k. How can we get the cube of a signal? Well, the cube of a signal Vx will be the square of Vx multiplied by Vx. Hence, if we cascade a squarer circuit with another multiplier, we will get the cube of the signal. The output of the first multiplier will be Vx squared by k and the output of the second multiplier will be Vx cubed by k squared. Thus we have generated the cube of the signal. This concept of cascading multipliers to generate higher integer powers can be extended to any power. We generally donate an integer power generator with the following symbol. It's the same as a multiplier, with the exception that we mention the power it generates inside the block. The output of the integer power generator is Vx raised to n by k. Next, we'll see how we can use these power generators to make frequency multipliers. First we have the frequency doubler. A squarer circuit can be used as a frequency doubler. Let the input be a sine omega t. The output will be a square by k into sine square omega t. Using trigonometric identities, this can be written as a square by 2k, minus a square by 2k, cosine 2 omega t. Hence, we have a signal with double frequency. We can get rid of the DC offset with appropriate filters. Now, we'll see how to make a frequency tripler. For this we need to understand two important trigonometric equations. The first one is sine 3 omega t is equal to 3 sine omega t minus 4 sine cube omega t. And the second one is cosine 3 omega t equals 4 cosine cube omega t minus 3 cosine omega t. Building a frequency tripler can best be understood with the help of an example. Suppose we have the input as 10 sine omega t and we want to design a circuit which gives an output of 10 sine 3 omega t. As the signal is a sine wave, we will use the first trigonometric identity. Substituting the values of Vx and Vout in the equation, we have Vout by 10 is equal to 3 Vx by 10, minus 4 Vx by 10 cube, which is 4 by 10 into Vx cube by 100. In other words, we have Vout by 10 equal to 3 Vx by 10, minus 4 by 10 into Vx by 10, into Vx squared by 10. It is clear from this equation that we'll need a cube generator and a subtractor. Hence, we cascade the both of them and the circuit looks like this. We cascade a squarer with another multiplier, both having a scaling factor of 10. The output of the squarer will be Vx squared by 10. The output of the second multiplier will be Vx cubed by 100. Hence, we're feeding Vx cubed by 100 and Vx to a subtractor. Using the formula for the subtractor, we get Vout by 10 is equal to R4, by R3 plus R4, into R2 plus R1, by R1, into Vx, minus R2 by R1 into Vx cubed by 100, into 1 by 10. Comparing these two equations, we get R2 by R1 equals 4 and R3 by R4 equals 2 by 3. So, if we choose R2 by R1 as 4 and R3 by R4 as 2 by 3, we'll get the desired output. Hence, we have successfully designed the circuit. Other frequency multipliers can be built similarly by using trigonometric identities. The next application is a divider circuit. We have two signals Vz and Vx and want to see what happens when we divide Vz by Vx. Here Vx should be a non-zero signal. We feed the required output as an input to the multiplier. V1 will be equal to Vout Vx by k. By using KCL at inverting terminal of op-amp, we get V1 by R1 equals minus Vz by R2. Hence, we get Vout equals minus KR1 by R2 into Vz by Vx. If R1 equals R2, we have Vout equals minus kVz by Vx. The next application is of a square root extractor, which can be obtained from a divider circuit by feeding Vout to both inputs of the multiplier. Using the formula of the divider, we get Vout equals to minus kR1 by R2, into Vz by Vout. Rearranging, we get Vout is equal to square root of minus kR1 by R2 into Vz. Take a look at the negative sign in the equation. We know that a negative value cannot be under the square root sign. Hence, Vout will be real only if Vz is negative, meaning that the square rooter is a one-quadrant device. The input cannot assume any positive or even zero values. To generate the nth root power of an analog signal, we can replace the squarer in the feedback path by the nth power generator. Now, we'll see how we can measure the root mean square of RMS value of a signal. The RMS value is the square root of the average of the squares. This suggests we need a squaring circuit, averaging circuit and square rooting circuit. Hence, we first take a squaring circuit to get the square. Next, we cascade it with a low-pass filter which acts as an averaging circuit. At this point we have the average of the squares. Finally, we cascade this with a square rooter. Hence, we're left with the square root of the average of the squares, which is the RMS value. The next application that we'll discuss is the amplitude modulation circuit. We want to shift a sinusoidal message signal to a higher frequency, known as the carrier frequency. This can be done by multiplying the message signal and carrier frequency. This suggests that we will need a multiplier in the circuit. The circuit of the amplitude modulator is as follows. Suppose our message signal Vm of t is Em cosine omega mt and carrier signal is Ec cosine omega ct. We'll refer to the message signal as Vm during the course of our calculations. Writing KCL at node A, we get simplifying this gives us. We have an inverting amplifier cascaded with the multiplier. Hence, using the formula for an inverting amplifier we have, Vout is equal to 1 plus mk into Vx. Combining these two equations and simplifying we get. Now, we substitute Vm as Em cosine omega mt. Hence, the output is 1 plus m Em cosine omega mt into Ec cosine omega ct, which is the amplitude modulated version of the message signal. The last application we'll see is how to demodulate an AM signal. In the previous circuit, we saw we can modulate a given signal. Demodulating essentially means retrieving the original message signal from the amplitude modulated version. This can be achieved by multiplying one of the sidebands with the carrier signal. We can use a multiplier cascaded with a low-pass filter. Let's take the upper sideband signal V0 of t. Suppose Vy is the local oscillator signal giving the carrier frequency. Multiplying these two, we get. This signal essentially has two different frequencies in it. First is a lower frequency omega m and the other is a higher frequency 2 omega c. We want the omega m component. We can get this by using a low-pass filter. Thus we get back our original message signal. That's all for this video. If you have any doubts, feel free to ask in the comments section below. Don't forget to like, share and subscribe.